Graphene, the wonder material. Introduction: Honeycomb carbon. Graphene is a two-dimensional material that is ultralight, super strong, and very conductive. It's a one-atom thick layer of carbon atoms arranged hexagonally like a honeycomb structure. What's so unique about the honeycomb structure? Mathematical calculations reveal that the honeycomb structure found in honeybee hives is the best structure to achieve the highest strength with the lowest amount of mass possible. This inspired many man-made honeycomb structures with high strength-to-mass ratios such as football nets and shock-absorbing structures found in cars. Similarly, carbon atoms bonded in this hexagonal arrangement on a 2D plane has the highest strength-to-mass ratio of any material currently known to man. The first scientists to discover graphene gave the analogy that if you have a 1 meter squared graphene hammock, it can hold the weight of a 4-kilogram cat while itself weighing less than one of the cats. Whiskers. Graphene is found in nature in the form of layers stacked together called graphite. When writing with a pencil, some 100 to 200 thick layers of graphene are detached from the graphite rod and stick to the paper. Types of graphene. The properties of graphene can vary significantly depending on the type of graphene being used. Although the basic definition of graphene is a one layer thick of hexagonally arranged carbon atoms, there are graphene variations with multiple layers of stacked sheets and other chemically modifications that are also labeled as graphene for convenience. It's important that a buyer of graphene material can identify exactly the type of graphene being produced in order to have a better understanding of the expected properties and its suitability for the intended application. The types of graphene almost entirely depend on the way they are produced. Production methods will be discussed in more detail in later sections, but listed below are the main types of graphene and graphite nanosheets in comparison. Differentiation based on size. Monolayer graphene, multi-layer graphene, graphite nanosheets, graphite. 1 carbon atom thick, 2 to 10 layers of graphene, above 10 layers of graphene but below 100 nm, above 100 nm particle size. Differentiation based on chemical modification. Pristine graphene, doped graphene, graphene oxide, reduced graphene oxide, graphite oxide. Pure graphene with no chemical modification. Graphene that contains chemical impurities such as nitrogen. Oxidized version of graphene. Has applications itself and is also precursor to reduced graphene oxide. From exfoliation of graphene oxide. Has more defects and O atoms than pristine graphene. Precursor for graphene oxide or multi-layer reduced graphene oxide. You can find more details in the National Graphene Institute website, which is linked in the description. The properties of graphene. Why does graphene not have the same properties of graphite if graphite is just many layers of graphene stacked together, one may ask. When you have so many layers of graphene stacked together, the strength of the overall bulk material is as strong as the weak van der Waals forces between the layers and grain boundaries in graphite particles. The strong carbon-to-carbon covalent bonds in graphene are not utilized in graphite. Furthermore, thermal and electric properties are boosted when you isolate the graphene layers, as more electrons are free to move. More details about properties are found below. Thinnest possible material. 0D, 1D, 2D, 3D. Buckyball. Carbon nanotube. Graphene. Graphite. Graphene is a single layer of covalently bonded hexagonal carbon rings which has a thickness of approximately 0.34 nm. This means that less than 1 gram of graphene can cover an entire football field. This makes graphene an ideal candidate for nanoelectronic applications that are looking for new ways of miniaturizing devices and computing power. Strongest material known. Graphene is the strongest material currently known to man. It has an intrinsic tensile strength of 130.5 GPa, which is more than 200 times than that of structural steel 400-550 MPa. To put it in simple terms, a 1 square meter graphene sheet would support a 4 kilogram cat but would weigh only as much as one of the cat's whiskers. If you change the cat to an elephant balancing itself on a pencil, that would still not be enough to puncture through the graphene. The carbon bonds in the hexagonal ring structure of graphene are stronger than the carbon bonds in the tetrahedral arrangement found in diamond. Graphene is therefore stronger than diamond even though they are made of the same carbon atoms. Material: maximum tensile strength MPa. Structural steel A36. 400-550. Diamond. 2800. Carbon fiber. 6370. Graphene. 130,500. Flexible and stretchable. Graphene is very flexible, which makes it very attractive for flexible electronic applications. It can easily bend like a sheet of paper. Furthermore, graphene can stretch to 20% of its original size without breaking, which makes it very suitable in polymer composites. This illustrative video by the Graphene channel explains flexibility of graphene. https /bzggpoheptric. Transparency. A single layer of graphene has almost total transparency to light 98%. However, most applications such as transparent electronic devices require several layers of multi-layer graphene to be able to make use of graphene's electronic properties. This creates a dilemma because the transmittance of graphene film decreases as the number of layers increases. One may ask, at what point does multi-layer graphene become no longer transparent? Graphite with several hundred layers is obviously non-transparent, so where is the cut-off point? Schauenzu's team at the Precision and Microsystems Engineering Department at Delft University of Technology study the transparency of graphene with the number of layers. Transparent electrodes require at least 10-15 layers of multi-layer graphene. At this point, transmittance drops to approximately 70%, which is still visually transparent and is comparable to heat-absorbent glass. Above that, which would be renamed graphite nanosheets, the transmittance drops to 30-35% at 50-60 layers. Electronic properties. Electrons behave in a very unusual way when confined to a single plane of covalently bonded carbon atoms in the hexagonal arrangement found in graphene. They behave like massless particles that travel near the speed of light, called ballistic conduction or ballistic transport. This is because there is negligible resistivity on graphene's 2D plane with no electron scattering, as there are minimal defects and impurities. Reduced graphene oxide has more resistivity due to the presence of impurities and defects in the stacking of a few graphene layers. Therefore, the electronic properties are sacrificed in reduced graphene oxide to achieve higher production volumes. Graphene production methods. Top-down approaches. Top-down approaches of graphene production involve isolating graphene layers from graphite. Details of different types of methods will be described here. Mechanical exfoliation. The first method used to exfoliate graphite sheets was developed by the Nobel Prize winners, who use adhesive tape to repeatedly peeling off sheets of graphene. This method was very useful in first studying graphene, but it lacked scalability and control over the quality of graphene produced. Chemical exfoliation. The chemical exfoliation method involves oxidizing graphite to form graphite oxide, followed by reduction. Oxygen inserted during oxidation is forced out during reduction, which pushes the layers of graphene apart. The extent of oxidation can vary depending on the kind of chemicals used and reaction time. This method allows scalability but introduces defects and impurities to the resulting graphene product, named reduced graphene oxide. Ultrasonic exfoliation. Ultrasonic exfoliation of graphite in solution could be regarded as physical exfoliation. It's somewhere between mechanical and chemical exfoliation. Instead of using the force of an adhesive tape to strip off some graphene layers, this method utilizes the force of ultrasonic waves to cause layers of graphene to separate from graphite in solution. The resulting graphene is not chemically modified in any way, but it's a solution-based method that utilizes water and other chemicals such as acetone and special polymers that can interact with the graphite in the presence of ultrasonic waves to exfoliate layers of graphene. A rapidly growing graphene company, Graphene, has developed a method of ultrasonic exfoliation of graphene using only deionized water in a special reactor with ultrasonic waves. This resulted in large production of 6 tons of graphene per month without the use of any harsh chemicals or heat from a furnace. This could be the most attractive method in terms of scalability and purity of graphene without many process steps, high temperature or harsh chemicals. Modifications to this method for greater control over the number of layers of graphene and faster production rates is an area of active research. Bottom-up approaches. Bottom-up approaches involve assembly of carbon atoms using carbon precursor, control temperature and pressure, and usually catalyst material and inert atmosphere. They have the greatest control over the number of layers of graphene and the chemical composition, such as when producing nitrogen-doped graphene, but they struggle from difficulty of scalability. Chemical vapor deposition (CVD). Chemical vapor deposition involves using a carbon precursor in the vapor form, substrate with catalyst material, heat and inert atmosphere, for example nitrogen or argon. Plasma-enhanced chemical vapor deposition (PECVD). Plasma. Organic synthesis. Graphene applications. Energy storage. Batteries. Supercapacitors. Corrosion-resistance coating. Medical applications. Drug delivery. Flexible electronics. Electronic skin. Flexible solar cells. Smart textiles. Water desalination. Graphene and graphene oxide membrane for water desalination. Graphene oxide was shown to have high permeability to water but be impermeable to many other molecules. Reverse osmosis has become the standard and cost-effective method of water desalination. Graphene oxide membranes. Graphene itself is not very permeable to water. But to work as a membrane without oxidizing it to graphene oxide, it has been shown that pores can be introduced with tailored pore size depending on the desired permeability. The latest graphene research. Research has never been more active in the field of graphene and graphene-based materials. New discoveries about graphene properties, especially when interacting with other materials, are still being made. Many new applications are getting discovered, as well as improvements on current graphene applications all around the world. The latest graphene research. Research has never been more active in the field of graphene and graphene-based materials. New discoveries about graphene properties, especially when interacting with other materials, are still being made. Many new applications are getting discovered, as well as improvements on current graphene applications all around the world. A lot of attention is given to researching more scalable ways to produce graphene and graphene-based materials and devices with greater control on the properties. A few significant examples of latest graphene research in 2017 are described below. Scalable graphene-based membrane for water purification. Large-scale graphene production by ultrasound-assisted exfoliation in supercritical CO2/H2O. Large-scale graphene production by ultrasound-assisted exfoliation of natural graphite in supercritical CO2/H2O medium. The current market for graphene materials and products. Largely, the graphene industry is still considered an emerging industry undergoing R&D efforts to improve the commercial scalability and application of graphene. However, there are a few companies that are already producing graphene and taking advantage of the growing market for graphene. During an interview, a representative from Graphene said that the current market for graphene materials is mostly in the area of composite materials and printed electronics. Image courtesy of NanoGraphene.net. The global graphene market revenue is forecasted to grow to $113.70 million by 2020. The main graphene challenges. The first main challenge with graphene is with commercial scalability. There are also concerns with toxicity. Also described here are some application-specific challenges, such as first-cycle irreversible capacity loss in lithium-ion batteries, scalability and environmentally friendly production. The main challenge for graphene commercialization is scalability. Reliable large-scale production of graphene with high quality and low cost is still an unsolved industry challenge. Progress in terms of scalability has been made in the area of reduced graphene oxide, but often harsh chemicals are used and quality is sacrificed with little control over the size of graphene, flakes, number of layers of graphene, and the presence of defects and unreduced oxygen atoms. The CVD technique described earlier is limited to the size of substrates that can fit inside reaction chambers, in addition to very high temperature requirements, 1000 Celsius, and long reaction time. Graphene oxide membranes formed by filtration method suffer from low filtration rates as water gets trapped between the layers of GO. Toxicity. One major concern with graphene, like any other nanomaterial, is its toxicity to the human body. Other promising 2D materials. The exciting properties of 2D carbon allotrope of carbon, graphene, caused many researchers to be interested to investigate other potential 2D materials with promising. There are three main candidates currently under investigation: transition metal dichalcogenides, phosphorine, silicene. Silicene is a two-dimensional allotrope of silicon with a hexagonal honeycomb structure similar to that of graphene. Silicene differs with graphene in that it has a buccal topology, whereas graphene has a flat topology because the coupling between layers in multilayered silicene is much stronger than in multilayer graphene. Silicene layers don't have pi stacking, which means that silicene does not cluster into a graphite-like form. Researchers observed 2D silicon structures in 2010 using scanning tunneling microscopy to study self-assembled silicene sheets deposited over silver. In 2015, researchers successfully made a field effect transistor made from silicene. The main advantage of silicene over graphene, especially in electronic applications, is that its buckled structure allows the band gap of silicene to be fine-tuned for the desired application. This is simply achieved by controlling the external electric field applied. 2D silica. Analogous to graphene oxide, silicene also has an oxidized form of silicene called 2D silica. Visit nanodex.com to buy your graphene.